Hello, Intermediate Algebra. Today we start section 8.4 where we will continue to work with quadratic functions. Today we're going to start talking about how we model with quadratic functions. So basically we're just doing more work with real world situations of quadratic functions. Okay, so let's look at this as the warm-up. It says this picture shows the height of a supply package dropped from the helicopter hovering above the ground. Okay, so they drop the package and then it's showing us the time after 0 seconds. It has a height of 350. After 1 second, 335, so on and so forth. The first question is, would a linear function be a good model for the data? So let's think about what a linear function is. We know that if we graph it, it would be a straight line. Okay, and we're going to graph it in just a second. However, we also can think back to what we learned. If we think about time as the x and height as the y, we can think about this like a table. And what we know about linear functions is that they have a constant rate of change. So if it's linear, both the x's need to change by the same amount. So they are going up by 1 every time, but the y's would also need to be changing by the same amount. When I find the difference between 350 and 335, it's actually going down by 15, but from 335 to 283, it goes down by 52. So because these are different, it does not have a constant rate of change, which means this cannot be a linear function. Okay, so then it follows up with, would a quadratic function be a good model for the data? We haven't learned anything yet based on what we're doing right now, finding rates of change. You will learn about that in the future. However, we could graph it. And when I plotted those points, this is what I got. And if I trace those points, I can see that it wasn't actually linear, but it looks more like a parabola. Okay, so yes, this would be, so this was my time. A quadratic model would be a better fit for this scenario because it is not linear, but as I look at the graph, I can see it has more of that curved shape like a quadratic would. All right, so now let's look at some other more algebraic ways of talking about quadratics. Okay, area. Area is often used when we talk about quadratics. This situation says a company offers rectangular pool sizes with dimensions as shown. Each pool includes a deck around it. If Carolina wants a 15-foot wide pool with deck, so the whole part, how many square feet will she need to have available in her yard? So this is a real world example. You want to put a pool in and you know exactly what you want, but you need to know what total amount of area you need. We've seen these types of problems before, so we're going to start by writing a function that represents the area. Okay, so I'm going to find the area of x equals, and I know that area is length times width. So we want the area of the whole thing though, okay? So what they tell me is that just the pool part we can see is x. Okay, but we have to account for the extra, this part that we want to add on the ends. Now it goes on both ends. We've done this before, but they're telling me the width of that deck is going to be +4. That's on each side. So for me to find this whole side length, it's actually x plus 8 because +4 +4. Okay, when we look at the bottom, or the other side length, right? So from here to here is 2x. The length of the pool is double the size of the other. But again, I need to add on the end the amount of deck space that we're putting on each side, which means the full length or width, whichever one you're going to call this, would be the 2x plus the 4 on each side, so 2x plus 8. Okay, so when I go to do my area, which is length times width, I need to use x plus 8 and 2x plus 8 to represent those. So my area function would be x plus 8 times 2x plus 8. Now that's factor form. We want to probably put it in the standard form. Typically that's how we like to look at functions. So we can use our box model if we want. We put the x plus 8 on the outsides because those are the factors, 2x plus 8 on the other one, and I multiply. I get 2x squared, 16x, 8x, and 64. So my model for area of this pool is 2x squared. I add the middle boxes, so plus 24x plus 64. Okay, so this is just my function that I can use. And now once I have that function, okay, so this is the same function, I want to now figure out how much total area does she need, or how much space does she need to make a 15-foot wide pool with deck. Okay, so if she wants a 15-foot wide pool, the width of the pool was just the x over here. Okay, so when they're telling me the 15-foot wide pool, they're telling me that x equals 15. Okay, so they're saying plug 15 in for x. Okay, so I take my function and we switched it to f. I'm going to call it a of x. A of 15 equals 2 times 15 squared. So this goes back to chapter 1. Remember when we're dealing with function notation, I guess chapter 3, the first chapter we did this year. Function notation means whatever value I want to have for x, I just substitute that in for all of the x's in the function. Type that into my calculator, and I found that the area for a 15-foot wide pool would be 874 feet squared. As soon as it's area, make sure you do that. Now, I quickly want to talk about just a side note. When you get to your Pearson practice, you will be asked to do a problem like this, but then it also asks you to graph it. Okay, so just make sure you remember that when you're asked to graph a parabola, you're following the steps of graphing standard form. Okay, so when you're asked to graph it in part B, you're going to take this, and as you learned in the last couple of sections, you would find the x component first by using negative b over 2a. Okay, so you'd say the h component is negative b over 2a. We'll write that down. So it's negative 24 over 2 times 2. So when I did that, I got negative 6. And then to find the k component of the vertex, this is again what you learned in the last section, or last couple sections, you would plug in the negative 6 for the x's. Okay, so just a quick reminder that you will be asked to do that. And when you go to graph it in Pearson though, so negative 8, so you would plot that point first, negative 6, negative 8 down here. But remember, you need at least a couple more points. So Ms. Brodigan taught you that you're going to make your table. You'd put your vertex. I like to put my vertex in the middle. Okay, because then we would find numbers on each side. So negative 5, negative 4 perhaps, negative 7, negative 8. And then you would have to put those back in. Okay, so this came up in the last lessons. I just wanted to show you that when you get to your homework, you will have to graph this one as part B. And last but not least, when you pick on Pearson, you want to pick the parabola. It'll look something like that in the tools. When you pick that, you plot the vertex first, and then I believe it makes you plot 2 more points. Okay, so in this case, I had negative 6, negative 8. I could then go to negative 7, negative 6. And then I always like to just plot the reflection of that. So I think Pearson only makes you plot that many points to be able to draw that parabola. Just a side note when you get to your homework. All right, so that's the first type of problem you're going to see from today's lesson. We're modeling area problems. And then the bigger new thing is this thing called vertical motion. So you want to make sure you get this in your book or in your notes, okay? So vertical motion model is used to model objects being launched in the air. So let's quickly watch this situation over here. Okay, so the diver diving off the diving board, jumping up into the air and back down is an example of vertical motion. Okay, so all right, so anytime you have vertical motion, this is going to be the equation that we use if the problem is in feet and seconds. Okay, so when you move on to other levels of math, you'll start to see meters per second. You might see that in some of your science classes as well. But in this class, we're only going to do problems with feet per second. Okay, so we're going to use the formula h of t equals negative 16t squared plus v sub 0 t plus h sub 0. And you can see that the v sub 0 and h sub 0 are going to be variables we have to fill in. They're different colors. So make sure you're getting this in your notes. The h of t, so what you're finding is the height of the object in feet after t seconds. You can see that that v sub 0 is going to be this thing called the object's initial vertical velocity. Okay, now in order to define something, we also need to understand what velocity is. And velocity is the speed of something in a given direction. Okay, so you're basically finding the speed. And then the h sub 0 is the object's initial height. Okay, so go ahead and pause the video and make sure you get this information down in your notes. And then we're going to move on and do an example. Okay, so here's an example. We just saw the little video of a diver jumping, and so here's an example of the math behind it. So this one says the diver jumps off a high platform at an initial vertical velocity of 12 feet per second. What quadratic function that represents the height h of the diver after t seconds of the dive? Or what is the quadratic function? Sorry, I forgot a word there. So again, we need to know that we're going to use that formula we just wrote down. And our job, once again, is to find the v sub 0. So again, I look at the problem, and it says an initial vertical velocity of 12, which means I'm going to plug 12 in for v sub 0. Okay, so I know that's there, but then I also need this thing called h sub 0. That's the initial height. Now, when I reread the words, I don't see anything about height. So sometimes it'll be in the word problem, but other times you have to actually look at the picture. Okay, so when I look at the picture, they're saying that this diving board is 30 feet in the air, which means that is the initial height. So again, when you don't find things in the word problems, make sure you're looking for pictures as well, just like we had to in the area problem. All right, so now that I know those are my things, I would say h of t equals negative 16t squared plus 12, because that's my initial velocity, t plus the 30, which is the initial height. So this is, again, just a way to get a quadratic function that now we can answer some questions about. Okay, so this is the function we're going to use. And now we're back to what you guys learned last section. Okay, so now we're going to answer problems about it. It says, how many feet above the platform will the diver be at the highest point of the dive? Okay, let's think about that in the picture over here. He starts right here, he jumps up, and then he starts coming down. Isn't it true that this is his highest point? And the highest point is the vertex. So the nice thing about this section is most of the work we're doing you've actually done before. We're just using it in different applications. Okay, so we're going to find what is that maximum height. Okay, now remember, when you have a standard form equation, in order to find the maximum height, we actually first need to find the time it takes to reach the max. And that's going to use that little mini equation that we learned, which is t is negative b over 2a. So we have to continue to make sure we remember that formula. Remember, a quadratic in this case is at squared plus bt plus c. Okay, so when we talk about the a, b, and c, the b is the number, it's the middle number. Okay, so the one attached to the t. So I have a negative 12 over 2 times a, well, that's the first number in the quadratic, so the negative 16. One suggestion I have when you do this is I usually change it to a negative 12 over, I do the 2 times negative 16, negative 32, and then I type that into my calculator. If you type it into your calculator when it's negative 12 over 2 times negative 16, you have to put the whole bottom in the parentheses or it'll calculate it in the wrong order because of order of operations. Okay. Negative divided by a negative is positive. It gave me 0.375. But remember, this is the seconds it takes to reach its max. So if you were asked the question, how many seconds does it take for him to reach his maximum point, that's your answer. This question, though, actually wants to know what is the maximum height. Remember, now that we found the x component, basically if we're talking vertex, that's the x, 0.075. We need the y component. So this is the time, the y component is always the height. So if I have an x value and I want to find the y, I use the function h of t, but now I know that I want to put 0.375 in for all of my x's. Okay, so it's that second step you can't forget to do to find the maximum height. Now I would just type all of this in one shot into my calculator. I'm going to assume we know how to do that. If you're not sure, make sure you're practicing it and asking questions of your teacher. But the maximum height that he will reach at his highest point is 32.25 feet. All right, one more example. I want you, oh, sorry, that's just notes that I talked about. Find the vertex, we talked about that. Okay, so last example, I would like you to pause the video, write it down, and try it all on your own, and then unpause the video to check your work. This one says, what is the diver's maximum height above the water if he dives from a 20-foot platform with an initial velocity of 8? So again, it doesn't give me the step-by-step here. It does give me the hint that this is the function that I'm using, which means first I need to find the initial velocity, the v sub 0. Well, that's going to be the 8. And then the initial height this time was in words. So my function is h of t equals negative 16t squared plus 8t plus 20. So that should have been your function. We once again want to know the maximum height. First, we need to find the time to the max. That's the t equals negative b over 2a. So you should have had negative 8 over 2 times negative 16. So it's a negative 8 over negative 32. You should add 0.25. And then in order to find the maximum height, you need to take that and plug it back into the original problem. Negative 16 times 0.25 squared plus 8 times 0.25 plus 20 is what you should have typed into your calculator, and I got 21 feet. Okay, so this time the diver went 21 feet in the air. All right, so today's lesson, we talked about area problems. Okay, so you need to find the length and the width, multiply them together, that gives you the area. And then we talked about vertical motion problems, okay, where you need to know this formula, be able to find your vertical initial velocity and your initial height, and then be able to find maximum heights and or the time it takes to reach its max. Tomorrow we'll talk about the third one, which is quadratic regressions. If you didn't get everything down, I would pause it right here to make sure that you get at least a couple of examples of each in your notes. This was the note sheet that I created. And then you are good to go. Thanks so much.